Petroff's equation. And to derive the Petroff's equation, I have considered a vertical shaft. Here you can see that it is having a vertical shaft which is rotating in a guide bearings. This is the vertical shaft which is rotating in a guide bearing, and this capital D is nothing but the diameter of the bearing. This is the diameter of the bearing. Okay, it is from here to here it is, and small d is nothing but it is the diameter of the journal. This is the diameter of the journal, or you can call it as a shaft, diameter of the shaft. This is small d, and here you can see that the c is nothing but the radial clearance. Okay, to find out the diameter of this bearing, diameter of bearing is from this point to up to this point. Therefore it is small d plus c, and here also we have a radial clearance, means it will be d plus 2 times c. It is radial clearance, both are in mm, and this is the length. L is the length of the bearing, and which is rotating. N is capital N is nothing but it is the speed of the journal, which is in revolution per minute, and this small n is nothing but speed of the journal, which is in rps, revolution per second. To convert rpm to rps means you need to divide it by 60. Okay, speed of the journal capital N, you have to divide it by 60, it will be converted into revolution per second. And z, as already you know, it is nothing but a dynamic viscosity or absolute viscosity, and its unit is pascal second or newton per meter square or newton second per meter square. Okay, now in this lecture I am going to derive the Petroff's equation. And before deriving this Petroff equation, there are some assumptions made by the Petroff. Okay, by considering these assumptions, we are going to derive the equation. And whatever the load which is acting on the bearing, okay, the load acting of the on the bearing is a small and light weight is acting. We'll assume that the load on the bearing is a small or the light load is acting, and whatever the leakage is there, okay, the leakage is negligible. If any leakages is there, it is neglected, and the clearance between the journal and the bearing is filled with lubricant. Here you can see that this is the clearance, and this clearance is filled with a lubricant or a oil. And whatever the viscosity is there, the viscosity is constant throughout the oil film. The viscosity is constant throughout the oil film. These are the assumptions made to find to derive the Petroff's equation. Okay. Now I am going to first find out the frictional force which is acting on that. Okay. How to find out the frictional force? First is to find out the frictional force. Frictional force. We know that tau is equal to F by A, or it is equal to Z into V by H. Okay, this is there in your data input, which is equation 15.1a, the frictional force. As we have discussed in the previous class, while defining the viscosity, that is dynamic viscosity, according to the Newton's law of viscous flow, whatever the shear stress is there, okay, the shear stress is how we got this equation 15.1a. Shear stress is directly proportional to the rate of change of velocity. rate of change of velocity, that is dv by dy. Okay, and this directly proportionality sign is, if you take that, it is introduced by a constant z, dv by dy. Okay, this is how you are going to get the equation. Already we have discussed that. You can go through that previous lecture, you will understand that. Okay, this is how I have taken the frictional force, and we know that shear stress is nothing but load by area, that is frictional force divided by area, and this is shear stress is directly proportional to the rate of change of velocity, which I have taken it from Newton's law of viscous flow. Now I can rearrange to get the frictional force. Therefore, frictional force F is equal to, it is Z into V, okay, into A, can take it A divided by H. Okay, and therefore we know that whatever the V is there, okay, velocity V is equal to, it is pi d n. Okay, pi d capital N by 60, or can take it as small n. Small n is nothing but it is in RPS. Therefore, V is equal to pi d n, and the cross sectional area, okay, A. Therefore, A is the surface area. A is equal to, it is pi into d into length of the bearing. Therefore, A is equal to pi d into n. Instead of d, I will represent in terms of radius. Okay, we know that d is nothing but diameter is equal to 2 times the radius. It is equal to 2 pi r into n. This is n, length of the bearing. This is the surface area, and the unit of area is mm square, and the unit of velocity is meters per second. Similarly, this h is nothing but the clearance. Here you can see that this is nothing but h. This is the clearance. H is equal to c, and the unit of this clearance, or h, is also in terms of mm. Now I can substitute these values, or whatever the velocity is there, area and clearance, in the above equation, that is the frictional force. Therefore, frictional force F is equal to Z into cross sectional area is pi d into L, and next is velocity is pi d n divided by h. H is nothing but c, clearance. Okay, this will be is equal to pi square into d square L n into Z divided by c. Okay, d is nothing but 2 times the radius. Diameter is equal to 2 times the radius. Therefore, it is equal to pi square. D is 2r square into L into n by n into Z divided by c. Okay, this will be 2 square is nothing but 4. It is equal to 4 pi square into r square ln into Z divided by c. And this equation is there in your data, and because if you see the unit of Z, okay, Z is nothing but the absolute viscosity or the dynamic viscosity. It is in Pascal second. Pascal is nothing but Newton per meter square. Okay, the unit of dynamic viscosity is, unit of this is Pascal is nothing but Newton per meter square second. Okay, the remaining, if you observe, the length as well as the radii, clearance, diameter of the journal or the bearing, all are in mm, except the dynamic viscosity. Means this has to be converted into square. Okay, I will write here all the parameters, all the parameters except the absolute viscosity, that is Z. Okay, that is its unit is Newton second per meter square. Except the parameters, all the parameters except this are in That's why you need to convert this in Newton second per square. Okay, for that, therefore, it will be F is equal to 4 pi square R square L into Z divided by C. Here it is Newton second per meter square. Meter square, you need to convert that into square. 1 meter is equal to 1000. Okay, here it is square means 1000 square means it is 10 raised to 6. Now, the unit of Z absolute viscosity or dynamic viscosity is in Newton second per square. If you take this to the numerator, if you take it to the numerator, it will be 10 raised to minus 6. I am going to take it to the numerator, it will be 10 raised to into 10 raised to minus 6. This equation is there in your data. That is the frictional force. That equation is 15.3b. Okay, and after this, now we need to find out the shear force. This is the frictional force, and there will be a shear force which will be acting on this. How to calculate the shear force? Okay, second one is to find out the shear force. Shear force. We know that shear force is nothing but frictional force divided by cross-sectional area. Now you have calculated or you know the frictional force. Got the equation. Substitute that in this case. Therefore, F is equal to F is 4 pi square into R square ln into Z into 10 raised to minus 6 divided by C. And here area is there. Okay, area, that is surface area, is equal to pi dl, or you can substitute as 2 pi R into L. Okay, into that is 1 divided by A. Area is 2 pi R into L. Here L will get cancelled, R will get cancelled with this. Similarly, pi, and this is 2 ones and this is 2 twos are 4. Okay, after all the cancellation, the remaining is, after all the cancellation, the remaining is tau is equal to, this is 2 pi R n into Z into 10 raised to minus 6 divided by C. And this equation is also there in your data, that is shear force. This equation is 15.3a, which is there in your data. And after the last thing is to find out the torque. You have calculated the frictional force, shear force. The last one is the torque on the journal bearing. Therefore, the third one is torque and we know that torque is nothing but frictional force into the radius of the shaft. Torque is equal to frictional force multiplied by the radius of the shaft. It will give you the torque. Therefore, torque is equal to frictional force multiplied by the radius of shaft. Substitute the frictional force. Whatever the frictional force you have calculated, that is equation 15.3b. Substitute that frictional force multiplied by radius. Frictional force is 4 pi square r square L into n z into 10 raised to minus 6 divided by c multiplied by radius. This will be r cube. Therefore, the torque is equal to 4 pi square r cube into L into n multiplied by absolute viscosity into 10 raised to minus 6. Already I have multiplied this r. So I am getting this as r cube divided by c. Okay. This equation is also there. That is the torque. Equation is there in your data input. That is bulbarity 15.3 c. And we know that the frictional force, that is when torque is there. Okay. Now we know that whatever the frictional torque is there, the frictional torque, that is T is equal to frictional torque is nothing but it is coefficient of friction. Okay, I will denote it by small f. In some of the textbook they are denoted as mu. Here I will denote it as a small f into W, that is the load, multiplied by the radius. Okay, this equation is also there in your data input. It is 15.3 d. Okay, now whatever the load is, the W is nothing but it is the load. Okay, you can see that whatever the load which is acting on the journal bearing. Therefore, W load is equal to, how you are going to find out the load? Load is nothing but the bearing pressure multiplied by the projected area of bearing. That is, bearing pressure is nothing but P. Okay, projected area is the length of the bearing into the diameter. Here you can see that bearing pressure is P, projected area is length of the bearing multiplied by the diameter. This is W is equal to P into L into D. So this is W. Okay, this can be rewritten like a diameter. We can replace this as 2r. Therefore, it is 2pr into L. This equation is also there in your data input. It is 15.6 C. Okay. And from the previous equation, that is the frictional force, here you can see that in the frictional force you can substitute the load W. Substitute this load in the frictional torque equation. Therefore, the frictional torque is equal to, substitute the W load. It will be 2F is nothing but the coefficient of friction into P is the bearing pressure into R square into L. Okay, this R multiplied by R, it will be R square. And from the equation, call this as equation 2, and we can call this torque equation. Where is that torque equation? Yes, This you can take it as equation 1. This is, we'll call this as equation 1. Okay. Now from both these equation, from equation 1 and 2, I am going to equate this. Equating equation 1 and 2. Equating equation 1 and 2. Equating equation 1 and 2. Okay. We have substitute the first equation. T is nothing but this equation. Substitute that whatever the torque which you have taken, that is equation 15.13 or equation 1. It is 4 pi square r cube L into N to Z 10 raised to minus 6 divided by C is equal to, substitute the equation 2, whatever the torque you are having, frictional torque, it is 2 into coefficient of friction bearing pressure into R square into L. Okay. In this case, some of the terms will get cancelled. Here, L will get cancelled. This is R square cube, means remaining is R. Okay. This is 2 ones are, and this is 2 twos are 4. Therefore, the remaining is 2 pi R into N Z into 10 raised to minus 6 divided by C is equal to F, that is coefficient of friction, into the bearing pressure, or we need to find out the coefficient of friction. Therefore, coefficient of friction is equal to, or here I have taken it as F, better to write F only, otherwise you will have a confusion. F is equal to, take this term to the left hand side. Therefore, it will be 2 pi, oh sorry, here it is square, pi square, it has to be pi square. 2 pi square R into N into Z into 10 raised to minus 6 divided by C into bearing pressure, or rearranging this equation, rearranging the equation. Therefore, the coefficient of friction is equal to, it is 2 pi square divided by, or 2 into pi square, 2 into pi square into 10 raised to minus 6 into Zn, Z into N divided by P, multiplied by remaining thing is R by C. R by C. This is the Petroff's equation. This is equation 15.48. Okay. In this, whatever this R by C is there, okay, whatever this parameter is there, it is called as radial clearance ratio. R by C is nothing but radial clearance ratio, and this parameter Zn by P is called as bearing modulus, and it is represented by capital C. This is small c. This is represented by capital C. It is nothing but bearing modulus. Okay, the above equation is the Petroff's equation for the lightly loaded journal pair. Here I will write where this the parameter R by C. R by C is called radial clearance ratio, and where the other parameter, that is Zn divided by bearing pressure, is called as bearing modulus, and that is represented as and this is represented by capital C. This is the required Petroff equation for light journal bell.